And not only do you have to hear me again, but the title of this talk is about code generation. I'm not going to talk a lot about code generation. That was a trick to get everybody to come. I'm actually going to talk about infrastructure. Infrastructure is boring, so I thought I needed to spice it up a bit. Specifically, I'll be talking about QAPI, QCFG, and some other frameworks that I've been posting about recently. I realized in the past year that you can get people to pay attention if you use fancy names for things, so I've been using lots of acronyms, and it seems to be working out pretty well. We're going to talk a lot about QAPI, but before we really talk about it, I wanted to talk about why we're doing all of this in the first place. Why am I focusing on infrastructure in QEMU as opposed to features? And it really comes down to, I think we've gotten to that point, as I was talking about earlier today, where we're reaching that million-line code mark where we need to spend more time with infrastructure instead of just focusing on features. And really, we need to talk about that a little more. So, as I've been saying many times, I really think QEMU is a project with good bones. I think that fundamentally we've got a good architecture. I think the problem is that we've gained a few 100,000 lines of bloat around the midsection in the past few years. We get a lot of features, but we have an appetite for the sorts of features that cross boundaries and break abstractions and really lead to bloat. So, over the years we've developed quite a bit of bloat, and we're going to talk about that in great deal. So, one of the problems is really KVM. We're so popular as a virtualization solution. We get so many requirements that we really haven't had the time to really spend, and it's hard to justify usually to go back and to rewrite things to make it architecturally cleaner. But I think it's something we have to focus more on. And for me, one of the big motivations, or one of the things that was sort of a wake-up call for me, was native KVM tool. And it's not about the existence of the project. There's actually been multiple alternative user spaces for QEMU. The only thing that really stuck out to me was that one of the initial justifications was that hacking on QEMU just wasn't fun. To me, that's really the wake-up call. QEMU should be fun. The reason I started working on QEMU was because it's fun. And I think it's not fun because a lot of the code is really hard to understand. And that's really the problem I want to solve. I want to make QEMU fun again. Okay, but before we can do that, we have to understand where the bloat is. We need to develop the exercise plan to work the specific sections where we need to lose some weight. So to start out with, I thought a good way to really talk about this was to take a very simple invocation of QEMU and then really talk about all of the moving parts that happen from doing that. This is a command line that I would typically use, but if you see the command lines that libvirt generate, they're much more complicated. So this is actually a simplification. That's the simplification. And these are just the user visible objects. So one of the things that I hope everybody appreciates is that libvirt is actually a really sophisticated project because they have to know about all of these individual pieces just to do something that simple. And we'll talk about the individual pieces. I don't think that this is wrong with respect to architecture because ultimately what we're doing is complicated, right? It just is. And this is the right general structure. These are the good bones. The thing that I think is the problem are all of these different islands, right? So it might not be evident here, but the yellow is the character device layer, the green is the block layer, and it's the fact that all of these things are individual islands as opposed to one common infrastructure that I think is really what has led to the bloat over the years. So let's talk about each of these sections and let's really understand what the problem is. So to start with the block layer, the thing I really wanted to talk about was just how do you interact with the block layer in QEMU? Well, we actually have currently 2 sets of options for creating block devices, likely to have a third by the end of the year. So there's the legacy -HDA commands, and then the legacy but not yet replaced drive command. There's also -device, which I didn't add here, but you can also create block devices through -device. And then we realize we're doing it wrong, so we want to introduce a generic layer via block dev. But then in the monitor, we have another set of commands. So drive add corresponds to the old style -drive option. And then we'll also have block dev add and block dev delete. We also have to have a mechanism to query. That's just a management interface. So there's 5 or 6 different ways to work with block devices from a management interface. But then internally, we also have a module system. This is probably one of the lesser known things about the block layer. You can actually configure QEMU to exclude individual block devices, individual formats, that is. You can whitelist individual formats. But that's all specific to the block layer. And again, it also has a factory interface. This is via block drive open. One of the things you'll notice is that we have lots of factory interfaces that do different things. And by the way, I do have a lot of slides, but please ask questions if there are any questions during the talk. I think it'll go better if people interact. The character device layer. So the character device layer, we only have 2 ways to create character devices instead of 4. So it's a little bit better, but that's because it hasn't gotten a lot of features historically. So we have the chardev option, which is a generic way to create character device backends via QEMU ops, which is one of our marshalling infrastructures. But very few people actually use that. The typical way of doing it is by executing like a -serial, a -monitor, -parallel command, and using a URI to encode it. There is some serious trickery in the factory interface for the character device layer to parse that URI, split out the type, and then figure out how to handle options. We also have a query character, a chardev, so that you can enumerate the character devices. And there's no dynamic registration, there's no whitelisting, there's none of that stuff for the character device layer. The display layer, everything is just straight open coded. So we have switch statements everywhere that if SDL, if VNC, there's no real infrastructure in the device layer. And I'm actually kind of sad to say that when I was creating these graphs, which was a really fun exercise, by the way, this is the layer that I really didn't understand. So even though I've been working in QEMU forever, I really didn't understand. I had to look at the code to see the relationship between all of these devices and how things were created. And to me, that's sort of the fundamental problem, is that when you have the amount of code we have, if there's not commonality between the subsystems, then there's no hope that we can work across subsystems in any meaningful way. The network layer. So the network layer is a layer that has gotten some love historically. And so we do have 2 ways to create devices, because typically you can tell the better maintained subsystems by how many different ways we have to create devices. So we have 2 ways to create devices with the network layer. The legacy -net, which uses VLANs, which is a crazy concept that has nothing to do with VLANs like VLANs. We do have netdev add and netdev delete. And we also do have a factory interface, but the interesting thing about the network layer is that even though we've got good modularization, there's no real way to compile things out in a robust fashion. And the network layer is sort of black magic in that, for the most part, it just works, and nobody really likes to touch it because it just works. It's got some fancy, some queuing stuff in it too. And then the monitor layer. The monitor layer is open-coded by the virtue fact that there's only one monitor. But it is an infrastructure, and it does have its own command line options, and it does have an HMP mode and a QMP mode and options, and that's all kind of invented from scratch. And then the device layer is complicated, but Marcus is going to talk about that later today. I'm not going to, I won't even get into that. But I think a good thing to point out is that for the most part, we are devices. That is what we do. The other things that we do are sort of just small pieces on the side. Okay, so let's drill down to what I would actually consider to be the fat. So every single subsystem, as we've just walked through and looked at, every subsystem needs some method of type serialization, because at the end of the day, when you create a device, you're giving a string. Maybe that string's JSON, maybe that string's a command line. At the end of the day, you create a device based on a string, and every subsystem needs to take a string and turn that into meaningful arguments. Every subsystem needs some form of inheritance. You can see the inheritance, hopefully you can actually see it, but in the case of the device layer, you have the E1000 inheriting from the PCI device. In the case of the network layer, you have like tap state inheriting from VLAN state. Even though we're C and C doesn't technically support object-oriented programming, we do extensive object-oriented programming in QEMU. So we have kind of limited forms of inheritance where we really suffer is polymorphism. So all of the different layers have some mechanism to have a base class and then invoke methods into a subclass from that base class. Where things get really complicated is that each layer has totally different semantics when it comes to like virtual functions versus abstract virtual functions. So if you don't implement a function in your subclass, the behavior of that can be anything from a segfault to just a default implementation or something crazier than that. And again, the problem is that it's just different everywhere. Properties. So whenever we query devices, so one of the things you saw in each subsystem is that you have some mechanism to enumerate what's been created. Well, you don't just enumerate which devices there are, but there are some properties of each of those backends or devices that also need to be enumerated. And it's convenient to be able to set properties of all of these devices. And again, this is an area where we're all over the place. There were just some patches on the mailing list recently to add an interface for doing block device properties that would be a mechanism strictly to the block device. We do have a way to set construction properties for a lot of things via QEMU ops. But where we have really nothing today and we do everything via open-coded functions is setting dynamic properties of objects. So if you want to change the link state of a device, or you want to modify migration throttling, these are all things that are open-coded and different in every subsystem. I mentioned object enumeration, and then factory interface is the other one. The number of functions we have in QEMU that boil down to either giant switch statements or big if-else blobs of parsing a URI string is really kind of phenomenal. And there's a real opportunity for commonality there. And then this last one is kind of is an important point too. So if you look at the whole diagram, one of the things you'll see is that there are links between all of the subsystems. So the character device layer has to talk to the monitor. There has to be some sort of interaction. The character device layer has to talk to the devices. For instance, they talk to the serial device and the parallel device. And likewise, the block layer talks to block devices. And there's just a lot of interaction between subsystems. How you create those interactions, how you tell a character device about the monitor or you tell it about a device model is totally different depending on the subsystem and how they're interacting. The way I like to think about QEMU in terms of what we do is that all of the command line options and all of the monitor options really are just creating this graph of objects. I mean, that is fundamentally what we are. That is fundamentally what our architecture is. And if we think of it as that problem, I think we can actually add a lot of commonality and really simplify what we do. Okay, so let's drill into some of these in a little more detail. And this is where we come back to QAPI. So QAPI was the first step in this grander plan of adding a good common infrastructure for QEMU. And QAPI is the type serialization part of the world. And the main observation with QAPI is that we should decompose serialization into two discrete parts. The first part is what I'm calling here a marshaller. And that's for a given C type, basically implement a visitor pattern. Such that if you have a struct that contains 5 elements, maybe A, B, and C, you can pass a function pointer to the marshaller, and it will call that function pointer on each of those structures. So ultimately, the problem here is that C has no introspection mechanism. The type system is too limited. There's no way to introspect on a type. All that marshallers really are is just a mechanism to introspect on C types. Now, with QAPI, we've actually written a simple IDLE compiler that can generate the marshallers for a given C type. And initially, the focus was QMP, that we would use that for all the QMP conversion. But as I said, every single subsystem has a need to do string conversions. So QAPI ends up becoming the general mechanism of doing string or type serialization within QEMU. And then the second part is the transport. So once you have a mechanism to introspect on types, and you can actually rationalize them in a higher order fashion, then you can separate out the process of going from that introspection to generating QMP, so this is JSON, or generating XML if you were so inclined, or even just command line options. Now, one of the things that tends to be missed when talking about serialization is that serialization is important in both directions. So one of the things that we don't do very well today is that while you can pass QEMU command line options to create objects, it's very hard to extract the right set of command line options from QEMU to recreate the same device model. Right? We kind of only support that single direction today of basically write only. We sort of have a construct-only device model for the most part. But there's a lot more here. So if you're interested, QAPI is the infrastructure in QEMU, and I encourage everybody to look deeper in this. Okay, and QAPI is there today. So we've already made that step in the direction of more common infrastructure. But that's only the beginning. So the next step that I really think we need to take is to introduce an object model that we can use throughout QEMU. So we already have a few types of object models today. The most prominent one is QDev. One way you can think of QEMU object model is generalizing QDev to be able to be used in the rest of QEMU. So the inspiration for the QEMU object model really was gtype and gobject. I actually looked very hard at reusing gobject, but for various reasons that didn't work out. So the QEMU object model supports inheritance. It supports only single inheritance plus interfaces. So interfaces are classes that have no state associated with them, so they're just methods. Very similar to the Java inheritance model or the gobject inheritance model, which is really where I took it from. It supports polymorphism at any number of levels, so you can have deep object hierarchies if you like to. That's something QDev doesn't do well today. So QDev can do polymorphism at one level. Once you start having class hierarchies that are deeper than one level, QDev really becomes difficult to use. It's class-based polymorphism, so you can't do monkey patching, so it's not like Python where you can overload individual methods. That might not seem like a big detail, but we actually do monkey patching in quite a few places in QEMU. I'm sure you wouldn't believe that, but it's true, we really do. Object properties really are kind of one of the critical features in my mind. And the implementation of object properties is actually in terms of QAPI. So that same visitor infrastructure that you use to do type serialization is how you implement properties in the QEMU object model, which means that you can set properties through any transport that we support. So you can set it via JSON, you can set them via the command line. There's quite a bit of flexibility here. There's standard object enumeration mechanisms, and also a standard factory interface. So instead of having a different way to create devices versus creating, say, a block device, you can actually use the same mechanism to create both, which I actually think is a really exciting property. One of the things that's a little difficult is the relationship between dynamic properties and construction properties. And this is an area that spent quite a bit of time on with QEMU Object Model. What I ended up settling on was this notion that construction properties are just normal dynamic properties. So you normally create a device without setting anything, with no explicit parameters. You then set the properties, and then you explicitly realize it, which is really the construction operation. This has a nice property that it fits our model a bit better. And then the last bit about QEMU Object Model is there are two special types of properties, a plug and a socket. And this really allows you to create that graph. So all that a plug and a socket really are a mechanism to say that I can connect to another device, and then for another object to say, I can accept another device. And that allows you as the user to build that graph dynamically. But let's talk about where we go from here, because I want to make sure we can cover this in the time we have. So QAPI is already merged. We've got that in the tree. We still have to convert all of QMP to it. Today it's only used for the guest agent, but I think we have a plan to do that, so I'm pretty bullish there. The initial QEMU Object Model patches are on the mailing list, so they're there to be reviewed. I've already begun converting the character device layer because this is a big infrastructure change. It's not something that's we can do all at once and be done tomorrow. So I think we have to divide the problem into smaller chunks, and I think the backends, just in terms of size, they're much smaller than the device layers. So if we focus on the backends initially, I think we can have a lot of success before really tackling the harder things. And then, as I've been talking to a lot of folks here, I think we really have to sit down and come up with a plan for how we can tackle the device layer, because I really do think we need to move away from QDev to something different. And I think we can do this in an entirely incremental fashion, where we take QDev as it stands today and then just add features to it until it is QEMU Object Model. I don't have that plan today, but I'm hoping we'll have it by the end of this week. And so then what do we do after that? And this is really what I think the big payoff is. So I think each of these improvements brings with it incremental value. But as we get to the point where we do have a lot of common infrastructure, I think there's an opportunity to really shake things up a bit. Today, the monitor interface has somewhere around 60 commands, I believe. This is the human monitor interface. It's actually a very complicated API. I think that we can reduce it to a much smaller number. So if we have a common factory interface for all objects, if we have a common way to query, we have a common way to set properties, a lot of the current commands just become redundant because they're just different views of the same thing. So I can see a world where all of our command line options, all of our monitor commands, or for the most part, are implemented in terms of just a few basic concepts. The other goal is that because the same mechanisms used by the command line as is used by the monitor, you can actually do all object creation, all initialization of the device through the monitor, which I think is a really important characteristic. I think that's a really defining characteristic of our next generation architecture in QEMU. Today we're very much focused around the individual command line user interface, and management tools are sort of a second thought. And I think this is what we need to do to turn our management interface into a first-class citizen. And then one of the most exciting things about having all of this is that our entire device model and our entire system becomes fully introspectable, so that you could actually do something as simple as dump the entire object hierarchy and the relationships to a config file, and then reload it on a different machine, and that's it. That's all you would need to do to create the same VM on two different systems. And that is certainly not the case today. It requires quite a lot of sophistication to recreate the same device model, particularly if you're doing monitor commands and PCI hot plug and things of that nature.
Yeah. Although you have the same ability through libvirt.
Right. So our complexity basically creates the need for libvirt to do amazingly complex things. Our jobs, our roles in life should be to make libvirt trivial. For the most part, we should try to simplify things for libvirt as much as we possibly can.
I can be a devil advocate. I do see a lot of value in it,
Yeah.
but being a devil advocate, I can imagine that QMU will be a really thin, low-level interface, while we do pass complexity and persistency to other layers on top.
Absolutely.
Because anyway, although if QMU will be that sophisticated, then higher level up to the user will be needed to know about PCI addresses, for example, the sophisticated users, not the regular one.
So, one way I view all of this is that if we got to this point where we had the common infrastructure for most of these operations, I think we could shed 200,000 lines of code from QMU. That's nothing but command line parsing, compatibility, dispatch, and things of that nature. So to me, this is about simplification, right? This isn't about adding more complexity to QMU. It's actually simplifying QMU, making it smaller and leaner. But this is the real critical thing, and I know I'm running short on time. When I talk about QMU 2.0, what I'd really like to do, and this is obviously a discussion that we have to have on the mailing list and in a larger community, is really deprecate a lot of things for 2.0. So if we can move to a common, to really get rid of that 200,000 lines of code, we really just need to remove some of the old command line options, some of the old monitor commands. And as we move towards 1.0, I think that if we start planning for deprecation, it's something we can reasonably do, probably 2 or 3 years from now. Obviously not tomorrow, but I think it's something we can reasonably do. And I don't think I have much time for questions, but I can certainly take at least one.